So today's topic is the important topic of linear transformations. So for a little while we're going to forget about the maps that we've been talking about, and we're just going to live and work in one vector space, our basic vector space, the underlying vector space. I'm going to call it V, and it's always this, as you know, it's the set. Every member of V is a vector, and I'll probably draw from Roman letters: V, W, R, S, T, etc., etc., etc. And of course, every vector space has their addition property. It's a real vector space, so scalar multiplication is in the real numbers. And we're not going to talk anymore, well, right now we're not going to talk about the dual space, or we're not going to talk about any tensor product spaces that may be out there that we'd be interested in. We're not going to talk about any of those for now. We're just going to talk about the vector space. And we're going to focus on the concept of the vector space's basis, which in this case we've written down as E mu. And remember, E mu is an arbitrary set of vectors from the vector space, from in here, that span the whole vector space. And we also have the added fact that in the dual space we define the dual basis with E nu under the principle that E mu E nu equal delta mu nu. That was just sort of, we'll review that concept about the dual space. But the point is that this guy, this basis is arbitrary, and there's many possible collections of vectors in V that can form a basis that span the entire space. Spanning meaning that if I pick a single vector out of V, and I'll call it, say, little w, I can write that in this form as long as E mu is a basis. But say I have another basis. Say I have a basis called F nu. It's also A nu, F nu. And this equality is really critical. The vector is always the same thing. The vector is an identity inside this, an entity inside this vector space. It is a vector. It is one of an infinite number of possibilities. But once I pick a basis, I can express that thing in terms of the basis. And if I take two different bases, the components are going to be different. But the difference is going to be compensated by the difference in the bases. Now, what needs to be understood is what's the relationship between this basis and that basis? That's the question we have to understand. The relationship between these two bases is a very, very important principle, and it's ultimately the foundation of the subject that's called linear transformations, and we're going to talk about that right now. All right, so to get at this question of how these two bases are related to each other, we're going to do an obvious thing. I'm going to write this basis in terms of this basis, and that's not a problem. Remember, these are vectors. Vectors live in the vector space. If you're in the vector space and there's a basis for the vector space, then that vector can be written in this form because that's the definition of a basis. Any vector in this space can be written in this form, including these vectors. So these vectors can be written in terms of these vectors, and these vectors can be written in terms of those vectors. And that's exactly what we're going to do. I'm going to write that the F0, the first of the second basis, the first vector inside the second basis, or the zero vector inside the second, the F sub 0 vector inside the second basis, is going to be, I'm going to give it a coefficient, and this 0 here is there to reference this 0 here. So this means that this is alerting us to the fact that this scalar is a scalar associated with some sort of representation of the 0 basis vector. And then I'm going to write out the expansion in this form. And what I've done is I've taken since basis vectors have an index, this scalar has got to tell me two things. First, it's got to tell me which of the new basis vectors it's dealing with, and that's the job of the lower index. And the upper index's job is to tell us which of the old basis vectors, or the E basis vectors, it's actually the scalar for. So it tells us, it's basically telling us both basis vectors that it's associated with. 0, 1, 0, 2, and 0, 3, like that. What's nice about using this structure is that in the end I can write 0, mu, e, mu. And when I do that, it looks a lot like this. It's got the Einstein sum mu, which is here, 1, 2, 3, 4, summed. Now it's just an Einstein sum, but I still have this one hanging on to tell me that I've got it for F0. And I repeat this for F1, which will be lambda 1 mu e mu. F2 will be lambda 2 mu e mu. And F3 will equal lambda 3 mu e mu. Notice that I can use mu each time, right? Because when you're doing this Einstein sum like this, these two are attached by being upper and lower and in the same term. There's no way to screw around and mix up these indices with these indices because they live in different equations. Or even if they didn't, they're in different terms of a single equation. These are called dummy indices, and we can do that all the time. So because it's a dummy index, I can use the same one. But this whole thing can be written as F, let's say, nu. Let me see if I can do a better nu than that. F nu equals lambda nu mu e mu. And this is a pretty important expression. This expression here tells us how these basis vectors are written in terms of these basis vectors. The mu, of course, indexes the new basis. The mu indexes the old basis. And what's actually important here is this is a matrix, right? This is a matrix, and this is actually a problem from linear algebra almost, right? Where this can be considered the components of a vector, this is a matrix, and this is the components of a new vector. And we're actually, linear algebra, the notion of matrices is based on this principle. In fact, matrices can be defined in terms of linear transformations inside vector spaces. That's one of the ways they were invented and the reasons they were used. Notice the way we've done the indexing here. There's a lot of different conventions out there for this. I like this one where you have this lower index on the left, upper index on the right. You definitely want sort of a row column setup, but you need the index to go up, otherwise the Einstein convention doesn't work. Linear algebra textbooks use a sort of a weird version of the Einstein convention where they duplicated indices are summed over, but they don't have to be up and down. So if you look at a linear algebra textbook, you would see a mu here instead of up there. But in most of the slightly more sophisticated work, you always see the down and the up. These objects here are not in any way to be understood as tensors. These guys could be understood as rank 1 tensors, however, but these guys are just a bunch of numbers that are adding a bunch of these vectors together, and it's a matrix if anything. All right, so now we're going to use this knowledge and put it to work a little bit to see how we make these basis transformations function. We have our vector space V, we have basis F mu, we have which equals lambda mu nu e nu, so there's two bases, E and F, and we have our vector W, which is in the E basis will be A mu E mu, and in the F basis will be B nu F nu, where again we're using dummy indices all the time. We're going to have a lot of work with dummy indices in this particular portion of the lecture. So we can use this expression. We can use our expression that converts from one basis to another, this collection of matrix elements. And by the way, these are actually matrix elements. I want to emphasize that this could be organized as F0, F1, F2, and F3. This is now standard linear algebra, right? And then this would be lambda 0, 0, lambda 0, 1, etc., all the way down to lambda 3, 3. And then over here, you would have E0, E1, E2, and E3. And if you do this matrix multiplication, you're going to end up with F0 equals lambda 0, 0, E0, plus lambda 0, 1, e 1, etc. This row will multiply with that column, and you'll get it exactly like linear algebra. So that's why I'm emphasizing these things here are not tensors, of course. They're matrices. And what's funny is this is a very abstract basis. We just called it E, and this is one we called F. But this we have to define in no ambiguous terms. We have to assign numbers for each of this. What's interesting is that the transformation is almost more real in some sense than the bases, which were just a collection of letters in our very simple vector space. That's all we can really do. But we can establish an unambiguous basis transformation called lambda, and that involves choosing these 16 numbers. Okay, let me erase this little digression here, and we'll go on to what I mean to talk about. Okay, so let's take a look at converting from this basis to that basis. So I'm going to write W equals B mu F. Well, I'm using nu, right? I guess I should stick with that. B nu F nu, which equals B nu lambda nu mu E mu. And now this is a scalar that represents, I've got that wrong. It doesn't even look right. You can tell this doesn't look right because the indices aren't matching, right? I've got this backwards. I should have nu mu like that because I'm summing over all of the basis vectors, so I need that Einstein sum pattern to match. So this here, this is a real number. This whole thing here is a real number, and that is these dummy indices here will go away. So it's a sum of a bunch of numbers, but in the end it's a real number, and you'll be left with one index that will contract over the E. And this is the expression of W in the E basis. But what's interesting is that I know what E is in the E basis in this case because I know that that has got to equal A mu. So I know that A mu equals B nu lambda nu mu. So this is actually a transformation to go from the coefficients in the E basis to the coefficients in the F basis, meaning I substitute this here and I got the coefficients in the F basis, and then I substitute, well, actually what I would have to do is I would need the inverse, right? That's the whole point. I actually am interested in this transformation. I want to learn how to get B into the A basis, right? And this tells me how to get A into the F basis. I want B into the E basis, and I've learned how to go from A to the F basis by looking at this fact here. But I can do it both ways, right? There's nothing stopping me. These are just matrices, right? So I can write, starting with this concept here, I can write E mu equals the inverse matrix, the inverse of lambda, mu, nu, F nu. And if I did this, I would likewise discover that B mu equals the inverse matrix nu mu A nu, like that. And so I've now shown how everything transforms. I know how to go from E to F. I know how to go from B, which is F, the coefficients of F to the coefficients of E. And I know how to get from the coefficients of E to the coefficients of F. And I know how to go from F to E, right? And everything works off of this one collection of numbers, right? Once I define this, because once I define this, the inverse is set, right? The inverse is just, you have to calculate the inverse. And, you know, that's not a hard problem in principle. It doesn't involve It doesn't involve anything other than a lot of number crunching, and there's a procedure. There's a procedure that gets you from any matrix to its inverse, as long as it's a square matrix. And this will always be a square matrix because every basis has the same number of dimensions. The dimension of a basis of a vector space is defined by the lowest possible number of independent vectors the lowest possible number of vectors to produce an arbitrary vector. And so there's only one lowest number. So the number of E's and the number of F's are always going to be the same. So this will be a square matrix. So it will always have an inverse. As long as this transformation makes sense, right? As long as this transformation makes sense, this inverse will always make sense. But now the issue is we have some objects which transform using the matrix that drives this basis transformation, and we have some objects that transform in the other way, right? Using the inverse matrix. And that is, in fact, all of the coefficients. The coefficient, right? The coefficients of the F basis transform using the opposite or the inverse matrix, while the basis vectors transform using the original matrix. And we have words for this, and they're very important words in the study of general relativity. We say that the basis vectors, F mu, they transform covariantly. And we say that the components, B mu, which use the inverse matrix, they transform contravariantly. And this is the origin of the words covariant and contravariant. Anything that transforms from one basis to another the same way that basis vectors themselves transform, using this principal matrix that we invented, those are covariant objects. And the basis vectors are covariant. It turns out the components to the basis vectors are contravariant objects, And in the end, let's see how this actually will work completely. So if I write down W equals B nu F nu, and that's going to go to, I'm going to first write down this term here. I'm going to write down, say, A nu inverse. This is very easy to mess up, so I want to be very careful. This is the transformation of the component using the contravariant component is being transformed using the inverse matrix. And then it's lambda, and I will establish a dummy variable for E. I'll say E delta, so I need a delta up here, and then ultimately it has to be a mu, like that. So, because I want to convert, I want to end up with E mu's, right? Or F mu's. This would have been F mu here, and this would have been B mu here, right? This is B mu, this is F mu. So now, what have I got? Well, if I look at this object, that is actually the product of two matrices. You know, the indexes in the inside here are matching, and they're inverses. So that object is going to be the delta function, nu delta. Shouldn't have chosen delta in this case, right? Because now delta is using double duty as an index here and as the delta function. But I think we can all see the difference, right? And then this will be E delta A nu, which basically ends up being A nu E nu. And of course that equals W, right? That's how W is defined back from the very beginning, right? Way back here. So what we've got going on is we now have, that's why things transform contravariantly and covariantly, right? Is to preserve this equality, right? This has to equal this in the end, And it does so because the transformations of the coefficients with the basis vectors exactly compensate. But what this ends up forcing us to understand ultimately is that things with indices that are in the up position will transform contravariantly using the matrices that are inverse to things which transform with lower indices, which transform covariantly. And the reason that the basis vectors are favored, right? They are the vectors in the vector space. They are the actual things we're kind of interested in. So when we think about transformations, we tend to say, oh, we're going to transform the basis vectors, and we're going to create a matrix to do that. And so those things that's the normal transformation. Everything else, if you transform opposite to that, well, you're contra, right? So it's just our preference for sort of leaning on the definition of the transformation in terms of basis vectors that gives us this word covariant, and things that go in the opposite direction we call contra. Now the problem, of course, is that in general relativity you never see the vectors themselves. As I've said in the previous lecture, they've come up with a system of index gymnastics that hides the actual vectors. So instead of seeing b mu, e mu whenever you're talking about a vector, you only see this. So you get introduced to things that are contra from the start, and they're the more important things too. So you don't, contra to what? It's like this weird language that pops out of nowhere. But now you can understand. They're contra because the thing that's missing, the thing that's hidden, the vector that's attached but kind of obscured, that's the thing that's transforming covariantly. So up indices are contravariant, lower indices are covariant, but it's a matter of sort of convention of language. All right, so that is the explanation for contravariance and covariance in terms of vectors. Now we're going to have to study how this works for tensor product spaces, and that will be our next lecture.